from UFSCar, and she's going to talk about topological classification of circle-valued simple Morse-Bott functions on orientable surfaces. Thank you very much.
Thank you. I will thank the organizer for the opportunity to attend this important event. This work is in collaboration with Erika Batista from Universidade Federal do Cariri and João Carlos Ferreira Costa from IBILSE Unesp. Okay, let's start. The characterization of a set of functions on a smooth manifold that satisfies a determined property involves two major questions. The first one is to get an invariant for particular function of the set, and how is the set of all the invariants admissible for these functions. So with respect to the first question, the classification problem of singular points of smooth math germs is an important problem in singularity theory. The classical classification is done by A equivalence. However, no local results are not abundant. So in this work, we are interested in the topological equivalence. So the definition is the following. Let M be a smooth n-dimensional manifold and P equal R or S1. So two functions f and g from M to P are said to be topologically equivalent if there exists homeomorphisms H from M to M and K from P to P such that K preserves orientation and F is equal to this composition map. So using the last definition, and when the target is R, Arnold, Prisliak, Charcot, Bolsinov, Fomenko, and others, studied the topological classification of Morse functions on surfaces. And recently, José Martínez Alfaro, myself, and Regilene Oliveira studied the topological classification of Morse-Bott functions on surfaces. Morse-Bott functions are a natural generalization of Morse functions, and I will talk about that in some minutes. When the target is S1, Prisliak studied the topological classification of Morse functions on surfaces. Batista, Costa, Nunes, Ballesteros, in this paper, in a particular section, they studied the topological classification of Morse function from S2 to S1. In 2018, Batista, Costa, and myself studied the topological classification of Morse-Bott functions from S2 to S1. So the idea here is to use the notion of Rep graph associated to the functions. So let's start with some basic definitions. Let M be a smooth closed manifold of dimension n, and f from M to R a smooth function. The singular set of f, denoted by this, is the set of all singular points of f. For each A in R, consider the level set given by the inverse image by f of A, and note that this set is a union of connected components called fibers. So a singular fiber is a connected component of a level set of f which contain a singular point of f. And then the Rep graph of a smooth function from M to R with isolated singular values is a graph obtained by contracting its fiber to a point, and the vertices correspond to the singular fiber of f. So for example, here we have the B torus, and the high function defined on it. So the rep graph of f is this, and note that the color dot here in the figure corresponds to the singular fiber of the function. So the idea here is to give the topological classification by topological equivalence of surjective simple Morse-Bott functions from M to S1. Here, M is an orientable closed surface without boundary. So first, we need to study the topological classification of singular level sets associated to F. They are homeomorphic to closed curve and edge of saddle points, and then use this information to give a good invariant. Okay, Morse-Bott functions. Let f from M to R a smooth function. We said that f is a Morse-Bott function if the singular set of f consists of isolated points and non-degenerate singular submanifolds. Excuse me? Excuse me? Too fast. Ah, okay, sorry. Okay, sorry. In local coordinated, we have that a Morse-Bott function can be expressed by this quadratic form when G is the dimension of the singular submanifold. Note that if D is equal to 0, then we have the expression of the quadratic form of a Morse function. So Morse functions are in particular Morse-Bott functions when the singular submanifold are homeomorphic to points. Now some more example of Morse-Bott functions. The first one is the round-Bott functions. This function is a smooth function where the singular set consists of a disjoint union of circles called critical loops. For example, if phi is a parametrization, of the torus in R3, and F if the projection in the z-axis, then we have that F is a round-Bott function where the singular set is the disjoint union of two circles, this and this. And the second example, we consider M the monkey saddle surface given by this parametrization, and the Gaussian curvature given by K is this expression here. Then it's possible to prove that K is a Morse-Bott function when the singular set is the union of the origin and this circle here given by this. Okay, consider the dimension of the singular submanifold and its index. The singular set of a Morse-Bott function from M to R can be subdivided in three subsets. They are the maximum or minimum point, the saddle points or singularities of index 1, and critical circumference or singular circles. So the behavior of this singularity is like you can see in the figure. And now, Okay, the local behavior of maximum or minimum point is easy to see. But the problem is, consider orientable surfaces. This set, they are the singular circle and an 8 formed by the union of the saddle point plus the separatrice associated to this point that they are called 8. In some minutes I explain a little bit about that. This 8 and this singular circle here, on surfaces they can embedding in different way. So we need to know how we can obtain the classification, the local classification of these singular fibers, the 8 and the singular circles. And then is the second part of my talk. Then let's consider M be an orientable class surfaces with genus at least 0. An embedded circle or a circle on sigma will be the image of an embedding from S1 to sigma, and a separatrix 8, or in short an 8, is the image of an immersion of S1 into sigma, homeomorphic to two circumference glued by a point P, and each component, they are the separatrices associated to this point, will be any of the two circumferences. So it's possible to prove that the closed regular neighborhood of an 8 on orientable closed surfaces can be homeomorphic to the sphere minus 3 digs, and in this case we said that the 8 is a planar 8, or homeomorphic to the torus minus 1 disk, and in this case we called it a toroidal 8. Okay? We will say that two embeddings, or 8, are topologically equivalent if there exists a homeomorphism from sigma into sigma that sends one of them in the other. The classification of embeddings on orientable closed surfaces is given by the following theorem. Myself and Martinez Alfaro and Oliveira proved that the number of no-equivalent embeddings on S of S1 on sigma is 1 if sigma is the sphere, or this formula here, other case. Then, for example, if G is equal to 4, sigma is the 4 torus, and the no equivalent embedding of S1 on the 4 torus are these. In fact, only there are 4, like here in the figure. The classification of 8 is given in the following theorem. We prove too that the number of topological type of 8 on sigma is 3 times G plus 1 if G is equal to 0 or 1 of this other formula, other case. For example, if we consider G is equal to 3, we obtain 12, 8 using the last formula. But here in the picture, we only can see 3. And note that these 3, 8 are non-topologically equivalent because the the complementary set with respect the surfaces here are no the same. So these 8 are no topological equivalent. Okay. And now I will talk about our main results in this work. Okay. Morse-Bott functions from M to R can be generalized to function from M to S1 using the following definition. A circle value function from M to S1 is called a circle value Morse-Bott function if for any x in M, we can choose a neighborhood V of the image by F of the point x in S1 and a diffeomorphism phi from V to R such that this composition map is a real value Morse-Bott function. So locally, a circle value Morse-Bott function is just a Morse-Bott function. The singular level set are singular circle, maximum or minimum points, and saddle points, the same as the case when the target is R. However, the global property of these functions are quite different from the classical Morse-Bott functions. For example, these functions on orientable closed surfaces can have no critical points. For example, the function here is from the torus into S1, given by the projection in the first coordinate. The singular level of F is like this, and then F has no critical points. But if the Euler characteristic of the surfaces is non-zero, then we have that a simple Morse-Bott function from M to S1 is always non-regular. Okay. And now we are prepared to give our invariant. So we consider a simple Morse-Bott function from M to S1, and we consider the following equivalence relation on M. We say that 2 points x and y on M are equivalent if and only if their image by F of this point are the same, and x and y are in the same connected component of this level set. So using this definition or using this equivalence relation, we can obtain the quotient space like this, denoted by R, capital letter RF. And this space admits the structure of a connected graph in the following way. The vertices are the connected components of level curve given by the inverse image by F of a point V. V is a point in S1, is a critical value of F, and each edge is formed by points that correspond to connected components of level curve, where V is a value in S1, and in particular is a regular value of F. So using this proposition, we have 4 types of vertices in our graph. Vertices of degree 3 associated to saddle points, vertices of degree 1 associated to maximum or minimum points, and vertices of degree 2. In this case, we have the black ones associated to regular values, and the white ones associated to singular circles. Okay? Well, it's possible to prove too that in the case of saddle point, it's impossible to have a toroidal 8. So from now on, we consider only planar 8s. And in this case, remember that a family of pair of regular circles, denoted by GS, intersect and define an 8, okay, that is surrounded by another regular level sets, this, denoted by GB. And then we need to put this information in our graph in the following way. We define a function xi that associates to each vertex of degree 3 in the graph the edge that contains the JB circle. We will indicate the effect of this function in the graph by a symbol, by a star in the edges. And then, using this function and the graph, we can prove that the graph plus the function determine the topological type of the 8. And now we can give the definition of our invariant. First, we need to consider V1 after that VR point in S1. They are critical value of F. We choose a base point V0 in S1 and one orientation. We can reorder the critical value such that the relation is considered here, and label each vertex with the index I between 1 to R, if it corresponds to the critical value Vi. So the graph previously defined together with the labels, colors, and the vertices, and with the function xi has previously defined, will be called the Morse-Bott rep graph associated to a sample circle valued Morse-Bott function from M to S1. And we will denote it by gamma F. Okay? Some remarks here. The first one is, if F is not a surjective Morse-Bott function, then F can be regarded as a Morse-Bott function from M to R via stereographic projection. Then this graph is the same as used in my paper with Martinez Alfaro and Regilene Oliveira. It's exactly the same. If M is the sphere, then there is only one topological type of 8 on it. Then the function xi is not necessary in this case, and then the Morse-Bott graph introduced here coincides with the graph given in my work with Batista and João Carlos Ferreira. The regular vertices in this graph distinguish between the case surjective and non-surjective. And the labeling of the vertices in our graph is not uniquely determined because we have two different orientations on S1. And now we need to decide when two Morse-Bott Reeb graphs are equivalent or isomorphic. So let f and g from M to S1 be two simple Morse-Bott functions and their respective Morse-Bott Reeb graph, gamma f and gamma g, and consider the quotient, and a structure on S1, the structure of a graph, whose vertices are the critical value of f and g respectively. Then we denote by S1f the structure of S1 according to f, and S1g the structure of a graph in S1 according to g. So f induces a quotient map from gamma f to this gamma f and gamma g respectively into this graph. And we say that two Morse-Bott Reeb graphs are equivalent if there exists graph isomorphisms, J from the Morse-Bott Reeb graph of these functions, and L from S1f to S1g, such that this diagram is commutative. Here, delta f and delta g are the discriminant sets of f and g respectively. And now we need to modify a little bit the definition of Morse-Bott functions that are topologically equivalent, because it's possible that homeomorphism between the surfaces send a singular fiber of f, for example, into regular fiber of g. So we modify this definition by the following. Two circle value Morse-Bott function g, f, and g from M to S1 are said to be topologically conjugated if there exist homeomorphisms h from M to N, k from S1 to S1, such that k preserve orientation, f is equal to this composition map, and h sends singular fiber of g into singular fiber of f. Okay? So our main result is the following. Given two Morse-Bott simple and surjective Morse-Bott function from M to S1, then we say that they are topologically conjugated if and only if their respective Morse-Bott Reeb graph are equivalent. So this theorem show you that our invariant is a complete topological invariant. It distinguishes between two Morse-Bott functions from M to S1 if they are not topologically conjugated, according to our definition. Okay. This is the definition. This diagram here is commutative. Okay. Oh, well, some example here to explain a little bit about our invariants. We have here two Morse-Bott functions from S2 to S1. In this case, for example, we have a surjective function from S1, excuse me. In the second one, it is no surjective function. So note that without these vertices, this and the other ones here, without these vertices, the graph will be exactly the same. So it's necessary to put these vertices in order to say if these functions are or no equivalent according to our definition. In fact, they are not, because one is surjective and the other one is not. So their Morse-Bott Reeb graph are no isomorphic or equivalent. Well, in the next example, we have here the torus and a projection defined on it into S1. Here we can see the singular fibers associated to these functions, a maximum or minimum point and a saddle point, exactly the same in both those figures. But note that these 8 formed by the saddle points are not topologically equivalent, because it's impossible to have a homomorphism from these 8 into the other ones if the closure of these separatists here is homotopic to 0, and in the first case here, both of them are essential curves. So it's important to distinguish these two 8 in order to have a good invariant for these functions. So with the star, we can distinguish the difference between these 8 and these other 8. So note that these functions are not topologically conjugated, and their respective Morse-Bott Reeb graph are not equivalent or isomorphic. So one remark here is the case when M half boundary is a work in progress. Maybe in Simpa and São Carlos we'll talk about that. I don't know. And that's all. Thank you very much.